And
That should be
all good.
I'll check on
Okay, it should be going now.
we are streaming on Rashad's account, right? Prolific.
We're streaming on we were streaming on last time.
Okay.
The other thing to make sure is that this works. Yeah, there's a video included.
Okay.
It's just YouTube, so it should be okay.
Can I see this? Wow, so it was before you swapped over, so now we are streaming.
Good. So there's just a lag being on it.
Yes.
That's fine. I assume there's usually a lag. Great, thanks. Yeah. Michelle, I don't suppose you've got a couple spare batteries on you, AAA. Clicker would work fine as well. I keep forgetting to change the batteries on this thing. Ah, blah. I will not sing. That's it. Hmm? Yeah, it's called Open It with Firefox. Yes, that's right. Fancy. Where'd you get the green laser one from? I'm guessing more expensive than the normal ones. Yeah, I just went through with the lazy approach. That's some serious lag.
That was
That's recording. This is some severe lag on that. That was what, 2 minutes ago?
Yeah, there is.
I'm ready. I know. Oh,
That just let me on desk. Like some of the list Yes. Yeah, someone's been wailing. I'm just here typing this.
hey. What are you doing? Breaking things.
It's always been my objective in quality. I said this now for as long as yes. I don't want to get I want to do anything to just make things worse and then the opposite. as much as they can towards themselves.
Sweet.
And it's easy to run the training process, or deal with escalations of credit scores.
Which was asked for the screen to be put there.
It's weird. There's
So
a bit
I think
something
you
like
can see
attractive,
something.
but I think there's a bit.
Because looking at that's annoying, looking at that's even worse. Right, evening everybody. You can't hear me in the back and forward, there's plenty of space, and I notice only my colleagues are sitting on the front row. Everybody else is too afraid. I don't pick on people I don't know, I promise. Maybe why they're sitting in the front row, I don't know. Anyway, this evening we're going to be talking about some swarm intelligence. So who was here for last month's genetic algorithms? Couple of you. Yes or no? It's not a hard question. It's not a maybe. You were either here or you weren't here. Okay, so genetic algorithms was the first of what are called the biology-inspired artificial intelligence algorithms. And swarm intelligence is the second. Please come in, sit down, plenty space, find somewhere. Wow. So decent attendance, just late. Maybe we should. Was it traffic?
Because you started late last time I came.
Cool. So next month we start at 5:45. Okay, so swarm intelligence is the second form of biology-inspired artificial intelligence. And in this case, we're looking at interaction between basically interactions between individual atoms that give us a collective behavior. And these are shamelessly stolen from Wikipedia. I probably should have cited them, but anytime we're talking about swarm intelligence, we're talking about lots of things. We're talking about lots and lots of small, individual, very simple entities with individually simple behaviors that collectively form a more complicated behavior from the interactions that they have with each other. So nothing in the system is particularly smart by itself. The complexity and the power comes out of the interaction between tens, hundreds, thousands of small, simple entities. There's three main forms, but this is an area where a week doesn't go past without somebody proposing a new fancy form of swarm intelligence. The problem is often it's the same old with an interesting new title shoved onto it. The academic papers are quite entertaining to read in this area. You find fancy new idea, go into the details and so on, but it's just that one again with the numbers filed off, a new title and a few small changes.
Publish or perish.
Or if you're in PhD, both. Preferably the publish first. They'd like you to perish after you've got the PhD, not before. It looks bad on the university's completion ratios. So the three I'm going to look at, and these are three of the better known, three of the more robust forms of it, are stochastic diffusion search, which gets a prize for the most unreadable wiki entry I've seen in quite a while. I had to read the top introduction paragraph 4 times before any meaning came out of it. It was English, but that's about all I can say about it. Particle swarm optimization, which I think still sends Rochelle into shivers every time it's mentioned, and colony optimization. Before we look at the details, the kind of things that this is used for. Routing problems are very, very powerfully solved with these forms of intelligence. Any form of how do we get from A to Z, scheduling, crowd simulation. Before we go on, I'd like to show you some crowd simulation. You've probably seen this before. It is fairly well known. It is here. Everyone heard of the massive engine? Anybody heard of the massive engine? Right.
A last alliance of men and elves marched against the armies of Mordor, and on the slopes of Mount Doom, they
Can we turn
fought
the
for
lights
the
off?
freedom.
Can we turn the lights off? Can we not? That'll do. Okay. So the lights will return in a moment.
Middle Earth.
This is probably the best part of it. With the exception of the first couple of rows that you can clearly see in the movies, this is obviously from the Lord of the Rings movie, with the exception of the first couple of rows which were real actors, all of this combat scene is done with what's called the massive plugin, which is a crowd simulation. Every single thing you see here, every single fighter, is just an AI object. The whole crowd simulation, the whole movement, the whole interactions, fully AI. All of this behavior.
Victory
Not a
was
very
near.
simple form. Okay. Thanks, Rochelle. Sorry about that. I'm sure we'll find the light switches one of these days. So that's crowd simulation, and it's actually been used a few more times in movies. It was used in one of the Batman movies for the bats. It's been used in some games. Very, very popular among 3D work because you don't have to individually design the movements of every single one of a 10,000 person army. You just give them some behavioral requirements and they interact with each other. It's kind of fun to actually go through the three of the big battles in the Lord of the Rings trilogy and actually look at the interaction between the simulated fighters. It is actually quite realistic. It's very simplistic, but it's quite realistic. Move towards enemy, don't just through the guy next to you. Simple stuff like that, and that is a form of swarm intelligence. Okay, so first up, stochastic. Oh, that. Stochastic diffusion search. I'm glad I don't present on this every day. Okay, once I did once an hour and a half presentation on statistics, and I mispronounced every single damn time in a different way, all the whole way through the presentation. Anyway, this is a search and optimization technique. Again, it's like all the swarm intelligence, it's based on crowds. What happens with this one is you've got a search space. You're trying to find a solution to a function, whatever it is. So you've got your search space. You scatter the individuals randomly across the search space, and each one forms a hypothesis based on where it is as to the solution to the function. And then it communicates with one nearby neighbor, and they exchange hypotheses, and the better one wins. Repeat this, and what you find is that you get a growing consensus as to what is the best solution. I say best because, like genetic algorithms, it is in no way guaranteed to find the absolute best solution. It's going to find you a good one. Is it going to find the best? Maybe. So, yeah. The analogy used for this one is imagine you and 9 friends were in a strange town for a week and you want to find the best restaurant in town. Well, all of you could go to each one of 20 restaurants, but it's going to take a while. So first night, send one person to each restaurant, or one person to each UK. Next day, everyone says what was the best restaurant they went to. Exchange of hypotheses, now you know you've eliminated a whole bunch, now you've got a smaller set. Repeat until you found somewhere good to eat. You're probably going to take 3 days to do that, as opposed to an exhaustive search. This is used for wireless network siting. What's the best wireless network to connect to in an area? It's been used for object recognition, which is quite interesting. Robot localization, so how does a robot tell where it is? Well, it can ask its neighbors and form a consensus as to where it is and what's in the environment. Particle swarm optimization. Michelle's not trembling too much yet. I'm not sending you to shivers anymore. Okay, particle swarm optimization, again, this is an optimization search technique. It's used a lot for function solving again. It's a simulated form of bird flocking, loosely defined as. What you do here again is send a whole bunch of individual particles out into the world, and their movement is based on a few very simple rules. Move towards a neighbor, but Stay away from, don't get too close to a neighbor. Move towards the average of the flock. Move towards your best known spot, the spot that you've seen and had the best function value, and move towards the swarm's best seen function value. And the various weightings that you give those different movement criteria affects the flock's behavior, and typically you'll see it converging inwards on a good spot. If let's say one thing sees the absolute best value, it will stay there potentially, or not move too far away from it, and it's pulling the flock's average up. So things move in general towards that. Again, not going to give you the absolute best result every time. There's a commonality in all of these. They're not exhaustive searches. They'll give you a good solution. They may not give you the best solution. A lot of the time you don't care. And colony optimization is an interesting one, based on real behavior events. This is used for solutions which can be boiled down to finding a path for a graph. Driving, route finding across maps, scheduling, trying to find out when to schedule things to suit as many people as possible. All those can be boiled down to a graph traversal. Take your individual particles and let them wander the graph at random, laying down markers as they go. In the real life, this corresponds to the ants' pheromones. These markers fade in time, and so the longer it takes to traverse a route, the weaker the markers are by the time the particle gets to the destination. Particles will preferably travel routes with higher marker values, re-emphasizing those more and more, and so you find that the best route gets heavier and heavier marked, and there's more and more things to traverse it. Very, very good for routing problems. I've seen some phenomenal routing problems where this just narrows in on a very complicated route very, very quickly. Right, so that was, in a very small nutshell, that was really, really fast. Swarm intelligence. I haven't studied this stuff extensively, so it's a fairly high-level discussion of it. Any questions on these? I know this was a rather shorter presentation than last time, I apologize. No questions? One shot, stand, horrified, confused. Okay. Quiet.
Well, what do you take you guys through the hackathon?
Stay Try to stay close to the laptop so Devin can play.
Okay.
Oh, sorry. That's why I was trying not to move you.
Cool. So for those of you, most of you weren't here last month, and we made the hackathon way too difficult. It was around optimizing drone deliveries from warehouses to delivery locations, with constraints on the types of packages drones could carry, and the goal was to create a genetic algorithm to solve that problem. So as you can imagine, Gail's talk was a bit longer to get into more detail around that, and the hackathon was a lot more complex. This time we decided to make it a bit more simple. I'll show you guys the cool. So if you guys go to this GitHub repository, this is the one we've been working on ever since the start of the AI meetup. If you want to catch up on some of the other hackathons and concepts we've covered, it's all up there. If we scroll down to number 8, which is today's Swarm Intelligence, you'll see we've got a very simple problem to solve here. It's around crowd control. Some concepts of what Gail was talking about. So if you look at this map, we've got stars which represent individuals, we've got hashes which represent walls, and the underscores just represent empty spaces. Your goal is to create rules for each individual based on their neighbors to optimize their movement to the other room. So we're seeing this on the left as one room and this on the right as the other room. You'll see there's 3 entrances, and you're trying to get all of these guys from one side to the other side with as few moves as possible. If you have heard of the intellect challenge in the past, it would sound familiar. We do a lot of problems that are based around this. There's a yearly challenge based around AI and intelligence where you do things very similar to this. So visit this link. It explains everything here. What you're going to be concerning yourself with are these two functions: the stopping condition and the making the move method. So if we look in the code here quickly, I've created a framework for you to play with. So it does a simulation for you. We've got some code around making moves in different directions. You would be analyzing what's in this map. It's a two-dimensional array of basically characters, if it's an individual, an empty cell, or a wall. But if you go down here, this is what you're going to be implementing: making your move and your stopping condition. So actually, while Gail was giving the talk, I thought I'd make a quick video.
Just to clarify the idea here, with swarm intelligence, none of the individuals are smart. So it's not a case of figuring out how to get one individual through a door. The individual shouldn't know very much. It's all about communicating with each other to try and get them across. So less about one person and more about what is the behavior of the entire group.
So here's a quick recording of what that simulation does.
Yes.
So at the moment, they're all making random decisions by themselves with the random function. They're either going north, south, east, west, and then the other four directions. Um, and that's a basis. So you've got a basis of individuals, you've got the two rooms. I've also made it so that you can play with some of the parameters and it will generate a map for you. So you can play with the height and width of the map, the number of individuals, as well as the door spacing. Based on the door spacing, there's a mod function used to determine how many doors should be in the map. So if you figure out a set of rules that perform really well on one map, good idea to try it on another map, because that's the whole point of AI and machine learning. It should be adaptable to different environments. For the guys in Durban, again, you can ask questions on the ZA Tech Slack group. We'll try and answer them, or just ask the facilitator, Thameshni, to WhatsApp us or something. Any questions around this? A lot simpler than last month. So hopefully you guys can have something working by the end of it. Oh, lastly, there's a few links here that we've included. That's some code implementations of some of the topics that Gail spoke about. So a lot of this is inspired by artificial life. If that interests you, I'd recommend having a look at Conway's Game of Life. There's a link to a Python example there. There's a PSO tutorial for Python as well, if you want to attempt a PSO for this problem. Also one for ant colony optimization. And lastly, there's a summary thesis of somebody's for crowd simulation with Python.
And there's a couple more academic links at the end of the slide deck, which are academic papers on material devices. They're a little dry, so that's academic papers in the stage.
Cool. And I think last thing I want to mention, if you guys are interested in image processing and image recognition, so we did a few meetups around those topics, as well as convolutional neural networks. I think we covered that as well. There's a cool competition on Kaggle. Kaggle's a website that hosts data sets and competitions around them. There's one in identifying or counting the number of seals in a picture. So if you're interested in that, it could be a fun challenge to take on. And then also I mentioned the Intellect Challenge. We're going to be launching that in the next few weeks, so keep your eyes out for that.
And one last thing, sorry. If you've got ideas for stuff that you'd like to see in the future, please let us know.
Yeah.
So at the moment we're kind of hunting through textbooks.
Yeah, I think from after this meetup, I'm actually going to send out a call for speakers I want some guys to give some talks on actual industry experience in using these techniques. So far, we've been giving you guys a sort of academic breakdown of what they entail, and then a toy example to try and implement it. But I think it'll be really useful to get some people who've worked with these techniques on real world industry or enterprise projects, and you might learn a lot from that. That's the template. So that's the framework that everyone's going to work in. So what we've done here is it's basically this file executed. So you work off this framework, and you'll see what I did is I said my stopping condition is never. It's while true. I actually have to quit the app by Control C interrupt on the terminal, and then make a smart move. All I'm doing is making a random move. What you want to do there is you want to analyze your neighbors, your closest neighbors around you, and make a decision based on what they're doing. But I think the links included here will give you some direction in terms of those heuristics. But the goal, the key thing, and why I think you should go look at Conway's Game of Life if you haven't, is actually I'll show it to you. These small rules, micro rules, create this complex emergent behavior, and that's the whole point of what we're trying to do with this hackathon. Was there a follow on? So here, Conway's Game of Life. So you'll see these complex artificially living organisms emerge from these rules. So there's an example of something called a glider gun. You get other things that are like spaceships and pulsing sort of life forms. Um, and this kind of stuff is useful. People have used it to simulate traffic and figure out how traffic lights should be placed in cities. Personally, I did a project on this while I was still studying to simulate forest fires. So it's really useful stuff. But what's amazing about it is all of this behavior comes out of these four rules. Any live cell with fewer than two live neighbors dies. Any live cell with two or three live neighbors lives. So these very simple four rules creates this very complex behavior. And that's the same premise of swarm intelligence. Basic rules of individuals taking their neighbors into account create complex behavior at a larger scale as them as a flock. Yeah, and that's about it from the hackathon side. You can always ask questions after we start.
So I assume two people cannot be at the same spot, right?
Yes.
And is there some like collision thing test, or we need to randomize?
There is a little bit. So if you ask an individual to move, it won't be successful if there is another individual or a wall in that target location. So I think, yeah, the collision, that's to what extent it goes to. As long as there's an empty cell that can move there. Um, the one constraint, just be careful of, it might crash the app, is adding more individuals than there are cells on the board. I didn't cater for that, but I can add it quickly. But feel free to ask about it while you're busy.
It said get move. Sorry. It said get move XY. That's so it only knows its location. How does it always they globe like across
There
the-
is a global access to the map.
It's a full map. So it
Yeah.
can do a global search if it wants to.
It could.
But that would be cheap.
Yeah.
It's not in the spirit of the game.
Solving this is actually trivial. I could do a star algorithm and path to the right hand side. It would take 5 minutes. Okay. It's not a point.
But it's
The
nice
idea
if
is
it only ask neighbors.
can you ask the nearest neighbors, singular, the entire swarm, who's the furthest to the right, so all sorts of things we could be considering. But yes, it's about can we, out of the behavior of individuals, extrapolate a more complicated behavior without things like a star and to the right-hand side.
So the interesting thing is, if you look at a flock of birds, birds close to each other sort of know what their neighbors are doing, but they don't really know what birds on the other side of the flock are doing. But you get this emergent behavior come out of it, and that's the goal with this. It was hard to build a framework for you guys to work in that's so constraining. Um, Also, I did this last night, so cool. Just shout if you guys have any questions. There's still some pizza, I think, and there's drinks in the fridge, so please help yourselves.